last time we were together, we took a look at absolute value equations. We solved these absolute value equations, which included an absolute value symbol and expression, by writing and solving two cases. If the absolute value was equal to, say, for instance, 5, we knew that there were two numbers that had an absolute value of 5. 5 and negative 5, we had to consider both cases and solve them both. Today we consider absolute value inequalities. First we're going to do is define that. Absolute value inequality is an inequality that contains an absolute value expression. That's a little circular, but let's look a little deeper into it. To solve it, we're going to write a compound inequality without an absolute value symbol. So our notes today include this chart, solving absolute value inequalities. And it gives us 4 different cases, which seems like a lot to consider, but when we look at them, we see that 2 of the cases are very similar. Absolute value ax plus b less than c, or absolute value ax plus b less than or equal to c. Similar, except for the inclusive inequality here. When we look at their equivalent form, we see that this looks very much like the and compound inequality that we solved prior to this in this chapter. When we look at the other 2 cases, absolute value ax plus b greater than c, or absolute value ax plus b greater than or equal to c, we can see that those include the word or in their equivalent form. We can see that that's an or compound inequality. Now lots of folks have some tricks or mental hoops you can jump through to try to keep straight which one is an and which one is an or, and that's fine. But I think we're maybe a little bit better off if we try to use our brains with this one, our common sense, and I think that will always guide us in the right direction. So if the absolute value is less than c, and we remember that absolute value is the distance away from 0 on a number line, the number's less than that absolute value, it's closer to 0 on a number line. So if I'm talking about positive 3, say, those numbers are less than positive 3. Going the other direction, if I'm thinking about negative 3, closer to 0 would be negative 2, negative 1, 0, greater than. So we can see that we're talking about 2 endpoints, say negative 3, positive 3, and the points in between, which is an and compound inequality. Similarly, if I'm talking about ax plus b greater than c, absolute value is actually farther away from 0 on a number line. Well, what kind of numbers are those? If this is positive 7, what's farther away from 0 than positive 7? 8, 9, 10, 50, greater than positive 7. And the same way with negative 7. What's farther away from 0? Well, these numbers here, negative 8, negative 9, negative 10. We can see that that looks like that or compound inequality, 2 endpoints and arrows going in the opposite directions. So let's solve a couple of examples. First, x plus 4 less than or equal to 9. Well, from our chart, we know that absolute value less than a number is going to be an and compound inequality. So let's think about how we're going to write this. We know it's going to be an and, so the value x plus 4 is going to be in between 2 inequality signs. In this case, less than or equal to. Well, less than or equal to what? Well, x plus 4, if it's less than or equal to positive 9, has an absolute value that's less than 9, so let's write that. Less than or equal to positive 9. On the other direction, if x plus 4 is closer to 0 than negative 9 is, x plus 4 is greater than negative 9, or negative 9 is less than x plus 4. So we solve in the same way that we learned last week. Subtract 4 here, and here, and here. So the algebra for our solution is negative 13 less than or equal to x, which is less than or equal to 5. Or we could say x is between negative 13 and 5 inclusive. What does our graph look like? Let's put together a number line. You can skip count by 5s on this one because the range is pretty large. 0, 5, and 10. Negative 5, negative 10, negative 15. Negative 13 is right about here. Negative 5 right about here. And the distance in between. If you'd like, you could pause the video and take a moment to try to set up number 2 on your own, and then check your work with me. Again, this is a less than absolute value inequality. So we know that this is going to be an and. 2x minus 5. It's a strict inequality of less than positive 10 and negative 10. Add 5, add 5, add 5, negative 5, less than or equal to 2x, less than or equal to 15. Divide by 2. Divide by 2, divide by 2. So negative 2.5 is less than x, which is less than 7.5. So there's our number line, open circles on those, and we're looking for the values in between. Okay, let's move on to another example. This time we can see it's a greater than absolute value inequality. This is going to be or. I need to write or. When we sat and looked at this in class today, the number one issue that we had is students either resisting or not recognizing yet that they need to write two different cases. So let's be sure that we do that. 2x plus 3, if its value is greater than 7, its absolute value is going to be greater than 7. So let's write that, 2x plus 3 greater than 7. The other possibility is that 2x plus 3 is less than negative 7, farther away from 0 than negative 7 is. So now let's solve these two. So we subtract 3 here and here. Divide through by 2. X is less than negative 5, or x is greater than 2. So on a number line again. A circle on negative 5 and an arrow left. A circle on positive 2 and an arrow right. And one final one, inclusive this time, greater than or equal to 5 plus x greater than or equal to 1, or 5 plus x less than or equal to negative 1. So less than or equal to negative 6, solid dot and an arrow, greater than or equal to negative 4. So these are some examples of how we would solve absolute value inequalities. Not only solving, but graphing as well.